Okay, so this video we are going to be introducing thermo. We are going to revisit some calculations that you last would have done, I guess in Science 10 when you did the climate unit and you looked at some stuff. So yeah, we're going to spend some time reviewing that as well as reviewing some other concepts. So we are now in thermodynamics. So thermodynamics basically is talking about the transfer of thermal energy or heat, okay? So a little bit different than the last few units. You're going to find we're going to get back into a lot of the math. So first thing we need to talk about is types of systems. Okay, we talked about systems when we were back in equilibrium. We talked about systems as either being open, closed, or isolated. So open, think of it as like a beaker on the table. Matter can enter, it can exit, and energy can enter and it can exit. Then we have a closed system. So basically you've put a lid on your container. So matter-wise, whatever matter you put in is more or less the matter you're going to end with, because nothing can enter or exit, right? You might change it from one thing into something else if you were doing a chemical reaction, but individual atoms would all stay the same. But energy can still enter and exit because you can still change the temperature. Okay, the last system we have is an isolated system. So isolated system, whatever you put in at the beginning is what is there at the end. So neither matter nor energy can enter or exit, okay? So we are going to talk about all three types of systems as we work through this unit. For the most part, our ideal system is going to be number 3, is going to be that isolated system. But there are definitely some times where we will use an open or a closed system, and it will be okay for our calculations just based off the set of conditions that we have. So next thing we need to quickly review is your laws of thermodynamics, okay? So first law of thermodynamics tells us that the total amount of energy in the universe is constant. Okay, you guys generally tend to know it as energy can't be created or destroyed. It can only be transformed from one type to another, or from one object to another, okay? And then the second law of thermodynamics says that in the absence of energy input, a system becomes more disordered. Okay, this is technically getting into entropy. We don't really tend to talk a lot about entropy. When you were in Science 10 and we talked about the second law of thermodynamics, we tend to more use energy moves from a hot object to a cold object. And you're going to see that we will definitely make use of that energy transfer throughout this unit. So, thermodynamics obviously relates to heat, which therefore relates to temperature. So it's important for you to remember that temperature is really a measure of the kinetic energy of a system, right? So the higher the temperature, the more energy our particles have. Generally, the faster they are moving, because remember that kinetic energy is 1/2 mv squared, right? So we're really kind of looking at how fast those molecules are moving, okay? So the sun. If you were writing the diploma, I'd be telling you right now, there's always a question that involves the sun. The sun is never a distractor. So it's important for you to remember as you work through thermodynamics that the original energy source for everything is the sun. Okay, you guys sometimes are like, oh no, it's like this other thing. But really all energy comes from the sun, right? Plants then transform that into glucose through photosynthesis. We are then able to extract energy from glucose through cellular respiration, right? And so are plants. Your general cycle through the whole thing is that animal and plant matter will then decay. It turns into crude oil. We've already talked about crude oil, how we can refine that to get hydrocarbons, and then hydrocarbon combustion is going to release that stored energy, okay? So I don't want to say don't get tricked, but please recognize that the source of energy is always going to be the sun. Obviously, yes, there are a couple of exceptions, and there's usually a few you're like, oh, but Miss Chip, what about this? What about that? We're not really super concerned about some of those other things. We are concerned with energy coming from the sun going through photosynthesis, okay? So you are going to find you need to know your photosynthesis and your cell resp equations. And we will talk about those in later videos. But those of you who have taken bio, you'll be like, oh yeah, I already know those, I'm good to go. Those of you who haven't are going to be like, what? I've only done physics. I don't know what photosynthesis or cell resp is. Pretty common to be asked, like, what are the reactants in one? What are the products in another? Is it endothermic, exothermic? Write the balanced equation. So definitely if you're not familiar with those equations, you are going to want to spend some time throughout this unit making sure that you are familiar with those, okay? All right, so now we're going to get into measuring thermal energy changes, okay? So we do have an equation for this. Again, last time you would have seen this equation would have been back in Science 10. It is that Q equals MC. Should probably type this instead of trying to use my finger on the trackpad. Delta T. Okay, so Q is standing for thermal energy. I wonder if I have this in the slide. No, I might have it in the next slide. Q is standing for thermal energy. So we can measure that in two ways. Let me just see what the next slide is. Yeah, okay, look at that. So we're going to skip slides around here. So Q equals MC delta T. So Q represents the heat or the amount of thermal energy. It's going to be measured in joules or kilojoules. You're also going to find it can either be positive or it can be negative. Okay, whether it's positive or negative is telling us whether a reaction is endothermic or exothermic. Okay, so if we see that we get a positive, that is telling us that this is an endothermic reaction. Whereas if we get a negative, that's telling us that this is an exothermic. Right, and if you remember back when we were in equilibrium, we were talking about Le Chatelier's principle, and we were talking specifically about temperature. I was kind of like, oh, look at those delta H's off on the side. Right now we really only care about the positive or the negative to tell us exo or endo. And I had mentioned that later on we would come into how you calculate those numbers. Well, this is the unit where we do that, right? So a positive Q value is going to mean that that particular process was endothermic. We had to put energy into it. A negative is going to mean it's exothermic and that it released energy as this occurred. So M represents mass. It can either be in grams or in kilograms. Okay, but what you're going to find is unit-wise, they have to be consistent. So if this is a joule, this has to be a gram. If this is a kilojoule, this has to be a kilogram. Okay, I can't mix and match and be like, I'm going to use a kilojoule and a gram. It doesn't work that way. So C represents the specific heat capacity of an object. So you will find that objects that are made of different materials are going to have different specific heat capacities. So specific heat capacity is basically if I had 1 gram of a particular sample and I wanted to raise the temperature by exactly 1 degree Celsius, how much energy would I have to put into that, okay? So some objects heat up really quickly, some objects take a lot longer to heat, and they are going to have different specific heat capacities, okay? So specific heat capacity, either in terms of joules per gram degree C or kilojoules per kilogram degree C, okay? You are going to find, again, just like I talked about up here, your units have to match. So either it's joules, grams, and joules per gram degree C, or it's kilojoules, kilograms, and kilojoules, kilogram degree C. Okay, can't mix and match them. You have to pick one and stick with it. Okay, you're going to find it when you watch the first lesson. We're often going to use the joules, grams, and joules per gram degree C. But then when we start getting into some of our bigger calculations, we're definitely going to switch over to the kilojoules and the kilogram, because generally when we're measuring energy involved in chemical reactions, it's usually a very large quantity, so we use kilojoules. So in your data booklet, you will find that there's that miscellaneous table. And on that miscellaneous table, there are, I think, 4 or 5 different specific heat capacities. I'll show you those real quick here. Okay, so this is on page 3 of your data booklet. You will see that in this miscellaneous table that we've used quite a bit, you actually have quite a few specific heat capacities in here. They give you the specific heat capacity of air, although we never really use it, so I'm not sure why they give it to you. And same with the polystyrene foam cup. We never really use those first 2. It's the next 5 that tend to be the ones we use. So copper, aluminum, iron, tin, and water. Okay, you're going to notice that all the units in your data booklet are given to you in joules per gram degree C. Doesn't mean you can't use them as kilojoules per kilogram degree C. It's just kind of the default that we tend to give it to you in. So if you want to change the unit to the kilojoules per kilogram degree C, the number itself is going to stay exactly the same. And that's because to convert the joules to kilojoules, I would divide by 1,000, and I would do the same for the grams to kilograms, but because one unit's on the top and one's on the bottom, it basically is me timesing by 1,000 and then dividing by 1,000. So that's why this unit is totally interchangeable. So if I was, let's say, dealing with water, I could either use a specific heat capacity of 4.19 joules per gram degree C, or I could use 4.19 kilojoules per kilogram degree C. So number stays the same, but you can definitely swap out the unit for the other one. Okay, can't do that for mass, can't do that for Q. You would actually have to be dividing by 1,000. But in this case, because you divide and then multiply by 1,000, it cancels each other out. Okay. If you're working through your booklet and you hit a compound that isn't in this table, but that you need the specific heat capacity for, just go Google it, okay? Obviously, it's a little different if the question's actually asking you to solve for it, then you should be solving for it. But if it's not, and you actually need that number and it's not in your data booklet and the question doesn't give it to you, and I think there are 1 or 2 questions like that, just Google it. Those are pretty accurate numbers, right? I know a lot of times your teacher's like, oh, don't Google things, you're going to get inaccurate numbers, like Wikipedia is awful. I don't want to say Wikipedia for chemistry really isn't that bad, but honestly, it's really not that bad because it's not. Chemistry isn't open to interpretation. It is or it isn't. So yeah, it's actually not too bad if you look there. Okay, so delta T is the last one to talk about. This stands for the change in temperature. So this is the other value that can either be positive or negative, okay? Some questions will tell you the temperature increased by 4 degrees C. Then you already know, oh, delta T is plus 4 degrees C. Or it could say the temperature decreased by 10. And then, okay, delta T is negative 10 degrees C. Sometimes, though, instead of telling you what the temperature change is, they're going to give you an initial temperature and a final temperature. And that's where you're going to have to actually calculate it. Sorry, this shouldn't be a capital D. That should be a delta, right? So it should be that triangle. So that should be that delta T. Sorry. My triangle drawing skills are off today. So it should be delta T is equal to the final temperature minus the initial temperature. So your temperature change is kind of what's going to determine whether a process was endothermic or exothermic, which should make sense to you because you think about Science 10, Chem 20, we were always like, oh, it feels hot, it released energy, it feels cold, it decreased or it absorbed energy, right? So yeah, we're going to find that the sign of our delta T is more or less what's going to determine the sign of Q, okay? So make sure you read the question carefully to see whether it is absorbed or released, because that's going to determine the sign of delta T. If you kind of ignore that, which sometimes you guys do, then you wind up with the wrong sign for Q, okay? So going back to the previous slide, don't think there was really anything in there that was specific that you needed to go over. I kind of talked about it all when I went through the next slide. Okay, so let's look really quickly just at a really simple example. Normally I'd be like, there's never a question on the diploma like this, but last semester there definitely was just that really simple, like, can you use Q equals MC delta T? So starting point, we want to start by writing our givens, just like we always do, right? So we were given a mass of 250 grams. I could choose to change this to kilograms if I want, but I'm just going to leave it in grams, which means my C is going to be that 4.6 joules per gram degrees C. I guess I should maybe read the question before I start listing out my givens in case I missed something. So it says 250 grams of ammonia, which then gives you the specific heat capacity for, is heated from 20 to 55. How much thermal energy is gained by the ammonia? So we got the M, we've got the C, and now we need to input that delta T. Let's see if I can find a delta quickly on this symbol list. Probably not, because it is an awful symbol list. It doesn't actually give you a lot of stuff you want. Just want a triangle. Here we go. I'll use that triangle. Okay, it's a teeny tiny triangle, but whatever. Okay, so delta T. So in this case, I wasn't told what the temperature change was, but what I was given was the initial and the final. So we're going to do 55 degrees C minus 20. So I have to be careful with my significant digits. Okay, the reason I have to be careful is I'm not using either 20 or 55 in my calculation. I am using the delta T. So I have to make sure that I recognize how many significant digits my delta T has based off of the operation that I just did. So in this case, it's not a huge deal because sig dig wise, it's going to work out to be the same, right? So if we do 55 minus 20, we come up with 35 degrees C. So where I would have to be careful is if, like, let's say this was 55 and this was 50, then I would be coming up with 5 degrees C, and that would only have one significant digit. And so that would then determine that my final answer could only have one. So you are doing subtraction here. The rule for significant digits in subtraction is number of decimal places. So no decimal places, no decimal places, no decimals. I still have 2 sig digs, so I can assume 2 significant digits for this question because this had 3, this is 2, and that has 2, okay? But yeah, be careful because I know a lot of the time you guys go back to the original question, and sometimes it's deceiving when they've given you an initial and a final because those aren't always going to be what we actually use in our calculation. So another quick comment has to do with temperature, right? A lot of times when we start getting into these calculations, someone would be like, hey, why can we use degrees C? Last year when we did stuff with temperature, we had to use the Kelvin scale. Why can we use degrees C all of a sudden? And so the real reason why we can use degrees C is we're always just looking for the difference in temperature. If the difference in temperature is 0 degrees, then the Q hasn't changed, right? We haven't put any energy into it or pulled any energy out because the temperature has stayed constant. So really, that's why we're allowed to use degrees C. Also, we're getting the difference. If I were to convert both to Kelvin and then get the difference, it would be the exact same number. So we really don't have to worry about that, okay? So we have all our givens. We have our equation of Q equals mc. I'm just going to copy that symbol. Let me delta T. And then we're just going to plug some numbers in, okay? So the other thing you're going to find is sometimes we use the equation and sometimes we don't. Sometimes we just flip over to unit analysis. It's good to be aware of what the equation is, but it's also really good to make sure that you are still looking at your units and you're making sure that things cancel and give you what you want. And that's because you're going to see the further we go in the unit, sometimes they mess around with the units on that specific heat capacity because different things are going to sometimes give us that specific heat capacity a little different, at which point using MC and delta T isn't necessarily going to be important. Maybe we only need C and delta T. But if I look at my units, I would recognize that. But if I don't look at my units, I'm not going to recognize that. So we have 250 grams times the 4.6 joules per gram degrees C. And if you want to write this more the way you would with unit analysis, you can definitely put this as joules and then put it over and then put the gram degrees C down here. Okay, totally up to you. And then times our 35 degrees C. Okay, then we can go ahead and get our answer. So one thing you're going to find, generally with temperature, it's a good idea to make sure that you put your sign in. If it's positive, it's not a huge deal. It tends to be more when it's negative. If you're not really in the habit of writing that, you'll sometimes forget. So once you go to calculate Q, Q must have a sign, right? This is kind of like when we did redox, we talked about how you had to have a sign of either positive or negative. The same is true for Q. We either need a positive or negative. Not writing the positive doesn't imply that it is positive, okay? So this one is obviously going to give me a positive answer because I don't have any negatives in there. So we're going to do 250 times 4.6 times 35. So we're going to get 40,250 joules. Okay, significant digit wise though, I'm only allowed 2. So 2 options. Either I can switch to scientific notation Or what I can do is put this in terms of kilojoules, right? I could divide by 1,000, which then is going to make it 40.25 because I can only have 2 sig digs. I come up with plus 40. So either you could write plus 40 kilojoules, or you could write plus 4.0 times 10 to the 4 joules, okay? Either way works. So this is kind of your really simple calculation of just plug the numbers in and get an answer. The next thing we start looking at, though, becomes slightly more complicated systems where we're still using Q equals mc delta T, but we're using it to create a different equation, okay? And that's because a lot of the times we're not just going to ask you like, oh, how much energy was it? Or what's the mass? Or what's C? Or what's delta T? Usually we're going to talk about it in terms of heat transfer. So we're going to talk about it as you put these two things together. So like, let's say you have like a cup of hot tea, you put a spoon into it. The spoon drops by so many degrees. How much energy did it absorb, right? So we're going to be relating two different systems. So when you are relating systems, when you list your givens, you want to make sure you're reading the question carefully to figure out how many different things you have, okay? So make sure you read carefully to determine how many different things isn't really the best word. I don't really want to say chemicals either, but how many different, we're just going to go with things, you have either absorbing or releasing energy. Okay, we then want to group them so that when we list those givens, we're listing all the ones associated with one thing under that and all the ones associated with something else under that. Okay, a couple of other things you're going to find is then when you go to create these equations, you have to recognize that something is absorbing and something is releasing, right? If you think about that first law of thermodynamics, we said energy can't be created or destroyed. It can only be transformed from one type to another. Or in the case of thermodynamics, that energy is being transferred from one object to another. So because the amount of energy has to remain constant, what we generally find is that whatever energy was either absorbed or released by one object, which is why I'm using Q1, has to equal the quantity of energy that went to the other thing, right? Because otherwise I've lost energy and we can't lose energy. That would defy the laws of thermodynamics, but I can transfer energy. So whatever the numerical value of the first Q is, it has to equal the numerical value of the second Q. Sign-wise, though, one's going to be a positive and one's going to be a negative. And that's because one released energy and one absorbed energy. So to take care of the fact that they're going to have different signs, you're just going to throw a negative on one side. It really doesn't matter if you throw it on this side or you throw it on this side. But you need to throw a negative in so that these wind up actually equaling each other, okay? And again, why we can do this is laws of thermodynamics, right? Energy absorbed equals energy released. So a lot of the times I don't actually know what Q is, but that's okay because generally I know MC and delta T. So what I can do is I can change this equation to be that the MC delta T of the first object is equal to the negative MC delta T of the second, okay? So we then create this equation that we can plug some stuff in and solve for. So this is where we start getting into much bigger equations, right? And you kind of start going back to that algebra, right? Remember when we did equilibrium and we were solving for X? We're kind of going back to that. We're just obviously not, I don't want to say not graphing in our calculator, but a lot of the times we don't need to graph it in our calculator. Some of you still definitely choose to graph it, but you don't have to. So the other important thing that I want to make sure I mention, because sometimes I forget to mention this, is water. Okay, so water and solutions are some things to talk about. So why I want to talk about that is when we are dealing with water, you're going to find sometimes it's going to give you the volume instead of the mass. but that's okay because when it comes to water, 1 milliliter is equal to 1 gram. So if it told me I had 200 mils of water, sometimes you guys are like, oh, I don't have a mass, I don't know how to do this question, but you do, because 200 mils would be equivalent to 200 grams, okay? And the other thing, or I guess assumption I would say, that we tend to make when we are in thermodynamics is that solutions have the same properties as water. Okay, and I don't think we're really going to get into that too much in this lesson, but definitely some other lessons you're going to see that we have to make that assumption. And why we can generally make that assumption is if you think about a solution, the amount of solute particles tends to be pretty minimal. Majority are water. So we're going to assume that if we have a solution and it gives us the volume, we can do the same thing. We can say that a mil is equal to a gram. We're also going to assume that the specific heat capacity of a solution is going to be the same as that of water, okay? All right, so let's look at some examples of showing you how to relate to these things, right? And so this is where part of why thermodynamics gets a little challenging is each question is different based off the information that it gives you, okay? At first, it doesn't seem too bad because you're like, oh, this isn't bad, I'm just doing this. But definitely the further you go in the unit and the more different types of calculations we do, if you're not practicing, you generally tend to find a point where you read a question and you're like, I have no clue what to do. So really important to make sure that you are practicing these calculations. Okay, so this one does come out of your booklet. It is not question 1. I don't remember which one it is, but you'll see when you work through that very first task that's inside of the thermo booklet, you'll see this question. So up to you if you want to do it again, but you can definitely skip it when you're practicing things. Okay, so we have 50 mils of sulfuric acid is poured into a styrofoam container containing 150 mils of water, and the temperature rises 4 degrees C. So assume the specific heat of the mixture to be the same as that of water and neglect the container. How much heat was generated? So we're trying to solve for Q. So we need an M, a C, and a delta T. So mass-wise, if I had 150 mils of water in my container, and then I just poured 50 mils into it, I now have a total of 200 mils. So my mass is going to be 200 grams. Okay, delta T, it told me that it rose by 4 degrees, so it's plus 4 degrees C. Okay, it then tells me that I should assume the specific heat capacity is the same as water. And water is 4.19 joules per gram degrees C, right? And you have that in your data booklet. You can look that up if you're like, how was I supposed to know that? It is in there. Okay, then we have Q equals MC delta T. So we're going to plug these numbers in. So we're going to go 200 grams times the plus 4 degrees C, and then times that 4.19 joules per gram degrees C. I can make sure that my units are all canceling, right? This gram is going to cancel that. This degree C is going to cancel that. I am left with joules. Where's my calculator? Here we go. So 200 times 4 times 4.19. So significant digits, I can only have 1. So my calculator is saying 3,352. So again, this is in joules. I can go ahead and convert that to kilojoules and divide by 1,000. And I just come up with 3 kilojoules. But I should make sure I put that positive at the front because we always want to make sure that we have a sign at the beginning, okay? So similar to the last one, but a little different in that I had to combine the 2 volumes, right? Important to remember when you pour 2 things into a container, that that final volume is what you're looking for, not that individual volume, okay? So next question. This one's a little different. So if 100 grams of water at 90 degrees C are poured into 80 grams of water at 10 degrees C, find the resulting temperature, neglect the container. So this question is different than the previous ones, and that's because we have 100 grams of water that's at 90 degrees, and we pour it into a container that has 80 grams of water at 10 degrees. So basically we're pouring hot water into a cup holding cold water. So what's going to happen is the hot water is going to cool down and the cold water is going to warm up, right? Until they eventually both become that same final temperature. So in this case, we have two things. Technically, they're both water, but they are doing different things, right? The hot water is getting cold and the cold water is getting hot. So when we go about listing our givens, we want to list them as two separate things. So we are going to have the hot water, and then we're going to have our cold water. So when we start listing the things that we have, right, if we think about the hot water, we had 100 grams of that. So I was told it started at 90 degrees. So what I actually have for this is Ti, okay, of 90 degrees C. Okay, it's water, so I know the specific heat capacity is 4.19 joules per gram degrees C. Okay, we go back over to the cold water, right? We had 80 grams, so 80.0 grams, and we know that the initial temperature for this was 10 degrees C. And then obviously we know the specific heat for it is also 4.19 because it's still water. So what you're going to find is in this question, sorry, I'm having issues, we get to do something a little different because they are both water, okay? So now what's going to happen is we have to generate that equation, right? And so this is where part of the challenge of thermo is that you have to generate your own equations, right? We have that starting Q equals mc delta T, but you have to be able to use that and manipulate that to create equations that work for the information that the question gives you. So I have to be able to recognize that in this case, the amount of energy that's being released by the hot water has to equal the amount of energy being absorbed by the cold water, right? Because the energy has to go somewhere. In this case, it's being transferred from the hot to the cold, okay? So when we start generating that equation, we're going to have that the Q of the hot is going to equal the negative Q of the cold. Okay, like I mentioned before, it doesn't matter which side you put the negative on, but you are going to have to put it on one of the sides because this has released energy and this has gained energy. So they're going to have different signs, but the numerical value will be the same. Okay, right now I don't have a Q number, so I can't use just Q, right? But this is where, like I had mentioned in that previous slide, we can change it to be mc delta T of that hot is going to equal the negative mc delta T of the cold. So what I get to do in this question that I don't always get to do is I get to eliminate C. Okay, the reason I get to eliminate C is they both have the same specific heat. If they didn't, I could not do that. I would have to leave the C in. But in this case, because they are both water, I can get rid of C. Okay, and I'm choosing to do that because it's going to make this question a little bit simpler as we work through it. Okay, so I also don't know what delta T is, but I should know that delta T equals TF minus TI. So what I can do is replace delta T with those values. Okay, so going back into here. So we know that the mass of the hot water, looking at our givens, was 100 grams. Okay, the delta T for the hot is going to be the TF minus the TI, which we know was 90 degrees C. Okay, and then that's going to equal negative 80 grams times TF minus the initial temperature, which was 10 degrees. Okay, so what you need to recognize here is TF between these two is going to be the same. right? We're always going to find that when we combine things together, the final temperature of all the things that are in contact are all going to be identical. Because if they're not identical, the energy is going to continue to transfer from the hot object to the colder object until they are the same. So we need to solve for TF, okay? And this is where basically this starts turning into algebra, right? Like, although it says TF, you could basically imagine that this was 100 times x minus 90 equaling negative 80 times x minus 10, right? It's the same thing. We're just using symbols instead of x as we go about solving this, okay? So steps are going to be the same as you would take if you were in math. We need to multiply this through, and then we're going to have to isolate TF so that we can go about solving for it. You're going to find I'm going to write every single step out. Some of you are going to be like, why is she writing every single step out? And that's because, as you guys know, as soon as I don't write a step out, usually half of you are like, whoa, what just happened? So I will write every step out, but you don't have to, right? You need to do as much work as you need to do to be able to solve for TF. If that means you're writing every single step out, you are writing every single step out. If it means you're doing a lot of this just like in your calculator, then you go for it. It really doesn't matter to me, okay? If we were in class and I was marking stuff, I'd basically be telling you marks for givens, marks for generating the equation, marks for plugging numbers in, and then marks for that final answer, and that the processing of how you got from here to there. Each of you may choose to take a different route, so it doesn't really matter to me, okay? So next thing we're going to do now is we have to start multiplying this through, right? So 100 grams times TF is going to give me 100 grams TF. Okay, then 100 grams times negative 90 is going to give me minus 9,000. This is going to have units of grams degrees C, right? Because we multiplied the grams here by the degrees C's over here. I left that in superscript. Okay, there we go. Okay, so this is going to equal, don't forget about the negative, that's at the front here. So negative 80 times TF. So I'm going to have negative 80 grams TF. Okay, then I'm going to do the negative 80 times the negative 10 that I have here, right? So that's going to give me positive, so plus 800 grams degrees C. Okay, so next thing I need to do is I need to isolate the TF. So this has TF, as does this. So I'm going to move this to this side, and this is going to move over to that side, right? We're going to swap some stuff around. So we're going to wind up with 100 grams TF. Because this was minus 80 on this side, when we move it to this side, it's going to be plus 80 grams TF. And that's going to equal, this is staying on this side, so 800 grams degrees C. And then on this side, we had negative 9,000, so we move it to the other side, it's positive 9,000 grams degrees C. Okay, so if you wanted to go right to the next step and skip this, you absolutely could have, right? You could have recognized that as soon as I move this negative 80 over, it's going to turn into 180 grams TF. Like I say, you just do what you need to do, right? And you could have recognized that 800 plus the 9,000 could be 98,000 grams degrees C. You need to write whatever you need to write, okay? Then what we need to do is to get just TF, we have to divide both sides by that 180 grams. So we can divide this by the 180 grams. And then obviously whatever we do on that side, we also have to do on the other side. So we're going to take this and we're also going to divide it by that 180 grams. Right now when we look at it, this is gone and we're left with just TF, okay? So we're going to do 9,800 divided by 180. And then from here, we get that TF is going to equal, right? These grams are going to cancel. We divide by 180. So we get 54 degrees C, because we can have two significant digits, okay? So basically it's math, you're solving for X, and that's what happens in thermo. Okay, I'm going to do one more example, just a slightly more complicated question. There are some sample diploma questions after this in your note package. I'm not going to solve those. I'll let you guys kind of solve those on your own. If you get stuck on some of them, by all means, send me an email and we can kind of work through some of those questions. Okay, so here's the last one I want to do. So now it says a metal container of mass 240 grams contains 60 grams of water at 25 degrees C. So 140 grams of water at 90 degrees C are added, and the final temperature is 60. Find the specific heat of the metal container. So this one is different because I now have three different things, right? If I look at this, I have the metal container. It's holding some water. I then have more water that I add to it, okay? So we have three different things happening. So when we list out our givens, we have the metal container, we have the water that was in it, which started at 25, and then we have the water that we add to it, which is at 90. So I'm going to call the water that was originally in it the cold water, just because it's at a colder temperature. You also could just call it like water 1, water 2, whatever you want to do. So we have the cold water, and then we have that hot water. So givens-wise, we have the mass of the metal container, right? That mass is given to us as 240 grams. Okay, we've also been given the mass of the cold water as 60 grams. And we are given the mass of the hot water as 140 grams. So we have masses for everything. So specific heat-wise, for the metal, that's what we're trying to find, right? It says find the specific heat of the metal container. So this is our unknown. Okay, this is water, so we know that the specific heat is 4.19 joules per gram degrees C. Okay, and then obviously the hot water is going to be the same. Okay, what do we have next? We need to find some delta T's, okay? So we know that the metal container and the cold water started at 25. So here's an assumption you always have to make. Whenever it tells you that something is in a container, you have to make the assumption that that container is at the same temperature as whatever is in it. Because it would be at the same temperature, right? If they weren't at the same temperature, there would be another energy transfer happening there. So when we look at this, what we're going to find is that the metal and the cold water, because they were always together, are going to have the exact same delta T. And that's because they're both starting at 25 and they're both ending at 60. So if we do the final minus the initial, we're going to do 60 minus 25. The delta T for both of those, oh, that's not in my little triangle mode anymore. So the delta T is going to equal positive 35 degrees C. Okay, and the cold water is going to be the exact same. Thought I had copy pasted that symbol. I did not. Let's fix that. Okay, so over here, we are now going to have a different temperature change though, okay? So temperature change for this one, that's going to be its final minus its initial. So the final is 60, right? Because the final temperature of everything is the same, but the initial temperature of this water was 90. So we're doing 60 minus 90. So I'm getting negative 30 degrees C. So for this question, we have three different things to relate. So we're going to have a Q1, which is the metal, Q2, which is the cold water, and Q3, which is the hot water. So you're going to find that we need to group them. Generally, how we group them is everything that absorbed goes on one side and everything that released go on the other side. The other way you can do it, just look at your delta T's. The things that are positive are going to get grouped together on one side, and the thing that's negative is going to go on the other side, right? If I had two negatives, those would get grouped together. So our equation that we're going to generate for this one is going to be that the Q of the metal plus the Q of the cold is going to equal the Q of the hot. Okay, and that's because the hot water released energy, and the energy that it was released was absorbed by the metal container in the cold water. So the one thing we still have to do, though, is throw the negative in. So generally, when you have a side that has something plus something, don't throw the negative on that side, because oftentimes you guys make a simple calculation mistake and you only apply the negative to the first thing instead of putting brackets around it all. So when this happens, put the negative on the side that only has one thing. Okay, it's going to make your life a lot easier. Okay, so similar to the last question, we don't actually know what Q is, so we're going to place this with MC delta T of the metal plus the MC delta T of the cold, and that is going to equal the negative MC delta T of the hot. So last question, I was able to get rid of the C because they were the same. But in this case, the metal doesn't have the same specific heat capacity, so C has to stay. I don't get to get rid of them, okay? So now we're going to plug some numbers in. So for the metal, we're going to have 240 grams. It's going to be times C because that's what we're trying to solve for. Then times positive 35 degrees C. Then plus the MC delta T of the cold water, so 60 grams times 4.19 joules per gram degrees C. And let me just extend the page. Okay, and then that is going to be times that positive 35 degrees C. And that is going to equal, hold on, I'm just going to shift this all over because I'm going to run out of space on that side, the negative MC delta T of the hot water. So negative 140 grams times the 4.19 joules per gram degrees C, and then times negative 30 degrees C. I'm going to shift that over just a little more so I can make some room for that. Okay, so now we gotta basically solve for C, right? So I'm going to do 240 times 35. So I'm going to get 8,400, and the unit of that is going to be grams degrees C, and then that's going to be times that C, right? Because we still have that in there, and this is what we are trying to solve for. And then it's going to be plus, and then I can do 60 times 4.19 times the 35, so 8799. When I look at this, the grams cancel and the degrees C cancel. So this is just going to be joules, okay? And this is going to equal, and then again I can multiply all of this through. Don't forget your negative, so negative 140 times 4.19 times negative 30. And that's going to give me 17,598 also joules, okay? So I need to isolate C, so I'm going to move this over to this side, right? Because currently it was plus. When I move it to the other side, it'll be minus. So I'm going to have 8,400 grams degrees C equaling that 17,598 joules, and then it's going to be minus 8,799 joules. Okay, and if you want to figure out what this is all in one step and skip this one, you definitely can do that. Again, I'm just writing everything out. So 17,598 minus 87.99, come up with 87.99 joules. So, oh, I lost my C. I was thinking something was missing here. Okay, there we go. There's the C. Okay, that is the one thing that does get a little tricky with some of these questions, is there's so many units. Sometimes for some of you, especially if you struggle a little bit with math, you may find that it's actually a little bit easier to just leave your units out. It does obviously leave you a little bit at risk of, if you misrearrange something, you may not notice because you don't have units, but it's also one of those where if you leave the units and then you're incapable of solving the question entirely, that doesn't really put you ahead either. So yeah, kind of got to do what you need to do based on your level of math skills. So now I need to be able to isolate this C, right? So basically what I'm going to have to do is I'm going to have to divide both sides by that 8,400. So we're going to divide, and we're going to divide by 8,400 grams degrees C, both sides, so that we can get rid of it on that side and get just what our C is going to be. So 8799 divided by 8,400 is going to give us 1.0, and I think we can have 2 sig digs looking at everything that we had, and that is going to have units of joules per gram degree C. Okay, so this is kind of the different types of questions you're going to see. You're going to see some that are really just Q equals MC delta T, plug it in, get an answer. You're going to see some that are 2 systems, right? So something absorbing and something releasing. And then you're going to see some like this one where there is 3 systems, right? We have the metal, the cold water, and the hot water. And we really have to look at that information to analyze how we're going to create that equation, okay? So it takes practice. The more you practice, the easier this unit is. If you don't practice, you definitely find you reach a point where you're just like, there's 3 different ways to solve for the exact same thing. How am I supposed to know which way to do it? And it entirely comes down to practice, okay? So practice the questions that are in your question booklet. You can also practice using the little mini quizzes that are up on D2L. Those are nice just because you don't actually have the answer. Sometimes when you guys have the answer, you rely on them so much that you don't actually know what you're doing wrong. You just immediately erase something and fix it. And so those can be a little helpful in that it's kind of a, wait a second, I should go back and try to figure out where I actually went wrong. Okay, so that is more or less your intro to thermo. Really important to make sure that you spend some time learning how to derive these equations, okay?